So thank you for this opportunity. Thank you for being here. Yes, so I want to speak of uniform temporal function, and the setting I'll have is much more continuous than in the previous talk, although there is some non-regularity involved. But the space will be a smooth manifold, or the time space. And on this manifold, I'll consider a cone field, quite general. So a closed cone field, let's say. I can view that as a subset of the tangent bundle of the manifold, which has the property that if you intersect it with a fiber, you get a convex cone. And say non-empty here. And it's closed. So the closeness is kind of a regularity, but it's quite a low regularity. So you can view that as a cone depending semi-continuously on the point X. So I'm not sure it's very interesting for you, but for me, it's quite interesting to have in mind that you allow the possibility of the cone being just a half line. So that's not probably very relevant for relations to globally Lorentzian geometry, but because I have a background rather in dynamics, I like to have this in mind, because then you can, for example, consider the case where C of X is just associated to a vector field, to a smooth vector field on the manifold. So what's the way I think of all this is kind of generalizations of IDs from dynamics. Exactly. So maybe let me mention from now on that everything I'm speaking now is joint work with Stefan Sour. Okay, so so when you have this, what are you considering? In the end, you are considering causal curves. They are the solutions of a differential inclusion. And because C is not very smooth, you have to consider curves which are not very smooth either. So what is nice is just to consider that the causal curve is a Lipschitz curve which satisfies this inclusion in the almost everywhere sense. So that's quite coherent with the classical definition of causal curves. So now, in this setting, what would be a temporal function? Well, so I prefer temporal than time because I'm going to focus here on functions which are smooth. That's what I like in this setting, and also maybe in the view of relations to dynamics, is that you have non-smooth data, but then you manipulate smooth objects around these non-smooth data. The temporal function is just a function such that ditto applied to the vector at a certain point should be positive whenever the vector belongs to the cone. I put a star to be clear that I remove 0. So the star downstairs means I remove 0. And I'll also use just the concept of causal function, which is just a function which is non-decreasing on causal curve. So this is kind of the maximal you can ask, I'd say, and this is kind of the minimal requirement in that direction. Just don't decrease on causal curves. So obviously, temporal functions are causal. So some remarks also on the setting. Well, a remark maybe worth being. It's just C with 0 removed. Nothing serious. So two remarks. The first one is that this inclusion is actually solvable, I mean, locally solvable. You can always, there always exists local solution of that. That's very classical theory of differential inclusion. This is related to convexity of the cone, right? So in a sense, whenever you have a curve which has a limit, you can extend the curve, which is the basic thing of these kind of things. And maybe second remark that I mentioned from now on is that I'll use a notion of enlargement of cone fields. So, so I will say that, let's say the cone field C tilde is an enlargement of C if C is contained in the interior of C tilde, and actually I put stars below to remove the zero section always, because you know there's always this problem that zero is not in the, well, zero is always in the boundary. Okay, you have a small problem which is not relevant with zero. What? Yes, yes, yes. So stars always means just I remove zero. So yes, that's a relevant question. It's more than asking that just for each x, C of x is inside C tilde of x. So for example, you can imagine examples, yeah, like you have like a vector in here and a vector here, and in between an interface when the cone would be bigger. And if you want an enlargement, it will be for an enlargement, you will need to have bigger cones on a small neighborhood of the interface, not just at the points where the cone was bigger for C. Okay. Yeah, yes. Besides, it will have it will have wider cones, but here very wider at certain points. Okay. So then a definition which is relevant in your community is that of globally hyperbolic. So C is globally hyperbolic if, by definition, well, there's no causal loop, meaning no closed solution of this differential inclusion. And I think the sets which are called emeralds, I did not define G+, but I think you see what it is. So G plus is the future of the set K1. So if I take two compact sets and I look at the emeralds, I think that's how it's defined. Associated, I want the intersection to be compact. Just a small remark, which maybe is not so important, but if you here just put the diamonds, the standard diamonds, and if you don't, and if you allow cones with non-empty interior, then you don't get the same definition. This is equivalent only if the cones have non-empty interior. But this one works perfectly well and has more or less the same consequences as the standard one. So a standard theorem in the field is that this is equivalent to the existence of a Cauchy temporal function. So and here Cauchy, so temporal I already said. Cauchy, what does it mean? Well, it's the classical definition. Cauchy means that the temporal function, if I compose it with an inextendable causal curve, I I get the whole real line. So if this is an inextendable solution. So what is the interval is not relevant because, well, as usual, this being a cone means the parametrizations of the parametrization of solutions is not relevant. Okay, and now comes the definition which appears in my title. So what we like are uniform. So actually, I'm sorry for the vocabulary is not. So uniform is what was called yesterday steep. For some reason, I thought steep was not good. And so it's also what has been called DG anti-Lipschitz. G is a Riemannian metric, yes. So definition, given a metric, a temporal function is called all this, but I will use G uniform just if d tau applied to the vector is greater than the norm of the vector for the metric G. And you can. Well, the anti-Lipschitz could be defined for non-smooth functions. I mean, but if the function is smooth, is equivalent. Okay, and why is this somehow useful? It's because if you are, as was noticed yesterday, if a function, a temporal function is uniform with respect to a complete metric, then it is Cauchy. So tau is said completely uniform if there exists a complete metric G such that tau is G uniform. And the remark, which was mentioned yesterday afternoon already, is that completely uniform implies Cauchy. Maybe I recall why, because it's very elementary. So you take a causal curve, a future-oriented, say, a half-causal curve in the future. If it's inextendable, so inextensible implies infinite length. If inextensible, with respect to a complete metric, right? And now, if you have infinite length and you have the inequality, which is T of tau of gamma of T minus tau of gamma of S, which is higher than the length of gamma restricted to the interval ST, which is basically what you get from this inequality, well, you see that at the T limit, tau has to go to infinity. Okay, so this theorem above, we extended with Stefan and also Ettore Mnguzi did it, that to the case of, to the existence of a completely uniform temporal function. So if C is globally hyperbolic, then actually for each metric, there exists G uniform temporal function. which in particular you can take a complete metric and then you find again the existence of Cauchy temporal functions. So the question I want to discuss now is what's the relationship between Cauchy temporal functions and completely uniform temporal functions? And actually, yesterday I realized that it has a strong relationship with the questions discussed around the null metric. So I would say that this definition is very related and probably equivalent in most settings to the question of whether the null metric associated to this time function is complete or not. So of course, the null metric in my setting is not defined, in our setting, should I say, is not defined always, because if you just have a vector field, you don't have a null metric. You cannot relate 2 points by any 2 points by causal curves. But if you specify a bit more the context to be in a context more similar to the one usually studied in Lorentzian geometry, then you can define a null metric, and probably this is equivalent. Okay, so the question is, what are the Cauchy temporal functions for which are completely uniform, which means what are the Cauchy temporal functions such that the null metric associated to them is complete? So we know that there exists one, but what about the others? So maybe I sum up, maybe I give some of what might be considered the main results in that direction. So the first one is that it is not true that every Cauchy temporal function is completely uniform. So there exists Cauchy temporal functions not completely uniform. And the second one is that actually completely uniform temporal functions are dense for the uniform topology in Cauchy temporal functions. So you can always approximate the Cauchy temporal functions that by completely uniform temporal functions. Maybe a remark about what this says, for example. So for example, there's a question which, when asked directly, is already solved, but the solution is not obvious, which is, if you have a Cauchy temporal function, is it still a Cauchy temporal function for some enlargement? So is being a Cauchy temporal function a stable property? So it's known. So I think it was proved by Bernal and Sanchez. But it follows obviously from this theorem. And the reason is as follows. So the first remark is that being uniform, a completely uniform temporal function is stable. And this is very easy because, so being stable means the property is satisfied by some enlargement in my language, in this language. So why is being uniform stable? Well, you want to preserve this inequality. You just need to take the cone defined like this. This defines an open cone field. No, sorry. I didn't mention it. This defines a cone field, which is an enlargement of my cone field if this is satisfied on my cone field. So I have obviously an enlargement. So and this is uniform with respect to the metric, let's say 2G or 4G, depending on how you. define that. So this is also completely uniform. This is uniform with respect to a complete metric, which is just a multiple of the original metric. So it is obvious that being completely uniform is stable. And then, what can I do? Well, I have, say, a Cauchy temporal function f, and I take a complete, completely uniform function which approximates it. Actually, I don't need it to be closely approximated. I just need that the difference is bounded. Yes? I will give one. It's not completely obvious, so I don't understand. I don't answer now, but I will give one. Yes, so you approximate it by a uniform function, and then you take an enlargement which has the following, which has two properties. One is that tau is still temporal, and this is easy that this is clear that you can do it. And one is that f is still completely uniform. Then for such an enlargement, tau will be still Cauchy. Because if you are a temporal function which is at bounded distance, which is uniformly bounded from a Cauchy time function, then you are a Cauchy time function. Actually, if you are at bounded distance from a Cauchy time function, you are a Cauchy time function, because going to infinity in plus or minus at plus and minus infinity is stable by bounded differences. So you obtain an obvious proof of this fact, which is not obvious to prove at hand from the original definition. So that's just a matter of saying that this contains some information. So let's say. So now comes the moment I expected from the start. So in France, we don't have these super things to erase boards. We always write on very dirty boards. Okay, so actually, in order to reach that, we studied intermediate questions such as the following. So let me define, again, a definition, a spatial hypersurface. So a spatial hypersurface is a hypersurface which has the property that it's transversal to the cone field on one hand, and on the other hand, it cuts an extendable causal curve exactly once. So once and only once. So, well, an easy property is that a level set of a Cauchy time function is a spatial of a Cauchy temporal function, sorry, is a spatial hypersurface. Now, the other direction is true also. It's a bit harder. I think it's also due to Bernal and Sanchez, if I'm not wrong. The opposite is true. So if sigma is spatial, there exists tau Cauchy such that sigma is a level set of tau. And now, for that kind of result, you can wonder, can I extend it to completely uniform function? And the answer is yes. So also holds. So tau can be taken completely uniform. Maybe, or maybe I don't. Yeah, I wanted to give hints of proofs, but I think I don't have much time. So maybe on this I go forward. So that's the first thing in that direction. I wanted to spend a bit more time on the second thing. So the second, of course, you could go that way. The second is I give myself two hypersurfaces. And can I make both of them two level sets of a Cauchy time function, a Cauchy temporal function? So I don't know if this question has been answered. Maybe yes. Yes? So, so if sigma 0 and sigma 1 are two spatial hypersurfaces, then there exists tau Cauchy temporal such that these are two level sets of tau. Of course, I want that they are in the future of each other. So sigma, disjoint, and sigma 1 is contained in G plus of sigma 0. So then there exists a Cauchy temporal function such that, well, sigma 0 is the level set tau equals 0, and sigma 1 is the level set tau equals 1. So same question. Yes, I think it's a theorem. Yeah, I know it's a theorem, but now I think it was already a theorem before we started to work. And so what I want to discuss a bit now is the fact it's always true in the sense of completely uniform. And okay, this is closely related. Maybe before proving that, I explain why it's closely related to this statement. Because the point is, once I know how to do it for two of them, I know how to do it for more than two of them. The tool works the same. So, right. Let me give a name to theorem at that moment. This will be theorem A, and this will be theorem B. Example. Yes, exactly. So what I claim is that not that theorem B implies theorem A, but mostly. The reason is the following one. Take tau Cauchy temporal function. Then define sigma I to be tau minus 1 of I epsilon, say. So I have closed leaves, which are the level sets, close to each other leaves, which are the level set of my Cauchy time function, the Cauchy temporal function. Then apply slightly better than theorem B to find a completely uniform function which has these level sets. So by theorem B plus, let's say, there exists F completely uniform such that F minus 1 of E I is sigma I. Yes? They will be diffeomorphic to each other. I don't require it. It's just a consequence of the fact they are level set of the same Cauchy time function, temporal function. So in the case where the cone field has an interior, I can take a smooth vector field inside the interior of the cone field, and then this smooth vector field will define diffeomorphism between different level sets. So, and then if you look at what you've done once you have this, it means that in this interval where tau takes the value, so tau takes values between I epsilon and I plus 1 epsilon, means that f takes values in the same interval, epsilon f. So this means that the difference between tau and epsilon f is bounded above by epsilon. So basically understanding how to find a uniform temporal function filling, what's the name of that? I don't know, a band like this between two temporal spaces allows to prove that. Okay, so now how can you, what's the idea of the proof? So I don't give the whole proof, but I explain the difficulty and I explain how we solve it. So what's the difficulty? The difficulty is the two hypersurfaces may go far away from each other, like this. So, of course, imagine we are in Minkowski space. We can go up as fast as v1, but still we can go up at finite speed, and so the distance between corresponding points gets high. So, in this drawing, you cannot have a function which is uniform with respect to the metric of the blackboard, to the flat metric of the blackboard, and which takes value 0 here and 1 here. Because if you want that the length of this curve is smaller than the difference between times at the extremities is not possible. So you will have to change the metric. And that's perfectly fine because the definition is not related to a specific metric. But the problem is, if you change the metric, so you are going to want to decrease the metric around here in such a way that this and this are not too far away from each other. But then it might be that if you decrease too much, then you can reach the infinity in that direction with a bounded length curve. That's the problem, right? And this actually occurs. That's the example I will give just after. But now I explain how we solved it. Basically, the idea is as follows. So you prove the existence of another spatial hypersurface, which is like this. So I'm sorry, this should not be very steep, but on the drawing. So these are not very steep. It remains transversal to the cone field. So my cone field is very narrow here because otherwise I don't manage to do the drawing. So this exists. It's not super hard to prove. And now the idea is as follows. You will take a metric which roughly is 0 everywhere and is very concentrated on this surface in such a way that crossing this surface costs 1. Now, to go from below to upstairs, you do it along a causal curve. You are going to cross this surface exactly once. So you are going basically to be able to do it in O of 1 of difference. And then if you work a bit more, you realize that you manage to be both uniform with respect to that metric. Of course, that's not a metric, but to that kind of metric, and take values 0 here and 1 here. But on the other hand, if you want to go to infinity, you have to cross the oscillations infinitely many times. So the infinity is at infinite distance. So this metric is complete. Okay. So that's the main idea in order to prove theorem B. It's okay. In more dimension, you have to. So the question is how to prove the existence of this thing. Yeah, you imagine this being radial in a sense. So the way we do it, take a piece here, and then take the past for some enlargement of our cone. It's going to be something like this. But it's going to intersect the other one because this is stably Cauchy. So this is Cauchy for the enlargement, assuming you take the enlargement small enough. Then you take a large piece here. Imagine this is a large compact set, and you do the same game again. And you obtain, like this, something which oscillates and kind of radially. Okay, so maybe now the last thing is the example. So the example of Cauchy not completely uniform. So let's work in R2 in the Minkowski 2 space. So my cone field is just the vectors Vx, Vy, such that Vy is higher than the norm of Vx, well, the absolute value of Vx. It's constant. I'll take the strip because it makes things a bit. So the manifold is actually not the full two space, but the strip y smaller than 1. So I take a strip and I have constant pointed upwards cones. Okay. So now let me first consider a function which is not temporal. So I consider a function phi of y, with phi is a map from -1 is a smooth function from -1, 1 to r, which tends 0 to 0, and which is onto. Right? Maybe a drawing would be. And I want, in addition, that's how it's going to happen, and I want that phi prime of 0 is 0. So the function is a time function. It's a Cauchy time function, but it's not temporal at the level set 0 where things are going to happen. No, sorry, it's not temporal, sorry. It's a Cauchy time function, not temporal. So of course, because it's not temporal, it's not uniform, because uniform is just quantitative way of being temporal. But that's not a counterexample yet because I was thinking of temporal functions, right? So I'm going to modify it. So I modify it by considering, maybe I still have room here. I'm considering another function. Well, I take it explicitly, which is going to be y divided by 1 plus x squared. So what I claim is that this second function, it's temporal. It's not Cauchy, but it's temporal. Why is that? Just because if you differentiate with respect to x, so you find minus 2x2y minus 2xy divided And it's easy to prove that this is bounded by 1. So this is smaller than 1 over 1 plus x2, which is equal to the differential with respect to y, my function. So it's tricky. So this is precisely saying, if you look at how I define my cone, this is precisely saying that the function is temporal. If I plug a vector which has a higher y coordinate than x coordinate, then the positive the positive term associated with the y coordinate is going to dominate the possibly negative term associated to the x coordinate. Okay, so now what I claim is that, so I have a Cauchy function, I have a temporal function. If I take the sum, I'm happy. This is a Cauchy temporal function. No? No, it does not. So yeah, so I take the sum and I obtain, and what I claim is that this one, it's not completely uniform. And why isn't it completely uniform? Well, I'm going to compute or to bound the length of the horizontal axis. So I have two vector fields. Let me give them a name, maybe V of x. V is the constant vector field 1, 1. So it's the right-hand side of my cone. And W is the constant vector field 1, minus 1. This is V, and this is W. So I want to go in that direction, and it's clear that I can bound from above the length in that direction if I bound from above the length of V and the length of W. The horizontal vector is V minus W divided by 2. So now, what can I say about V? Norm of V, so yeah, what norms do I compute? Here I compute the norm with respect to a certain Riemannian metric. So let G be a metric such that tau is G uniform. What I claim is that G cannot be complete. That's what I want to prove. Now I'm going to compute norms for G. What can I say? I say that the norm of V is smaller than dx tau applied to V. And I want to compute this on the horizontal axis. And this is bounded by 1 over 1 plus x2 times. Because it's going to be bounded from above by the norm of dx psi, by the norm of dx psi plus the norm of dy psi. The differential of phi is 0 here, so it does not contribute to this computation. So maybe it's very badly written. I'll write it again. Similar for W, it's exactly the same. So I'm done. The horizontal vector has norm which is bounded from above by a constant divided by 1 plus x2. So it means that the length of the horizontal axis is finite because this is an integrable function. And